Dear students, after studying this module, you shall be able to know what are aromatic nucleophilic substitution reactions, learn about the mechanism of aromatic nucleophilic substitution, identify the benzene mechanism, evaluate product formation as a result of aromatic nucleophilic substitution, and analyze mechanistic differences between addition, elimination and elimination-addition mechanisms. Nucleophilic substitutions on aromatic rings are relatively less common reactions that involve bond formation between aromatic carbon atom and a nucleophile along with bond breaking to the leaving group. The reasons for less reactivity of aromatic rings to undergo nucleophilic substitution is basically the presence of aromatic ring pi electrons. These pi electrons make the aromatic system an electron rich system that are more likely to be attacked by an electrophile rather than a nucleophile. Secondly, students, the aromatic ring loses its stabilization which it has gained due to resonance of 6 pi electrons if a nucleophile attacks, which it subsequently gains by the removal of the leaving group. Therefore, overall, under special substrate structure, nucleophile properties as well as special reaction conditions, aromatic substitution reactions, mainly nucleophilic aromatic substitution reactions, are facilitated, as we shall learn in this module. Now students, as I have introduced the topic of aromatic nucleophilic substitution to you, we shall now go into the study of details of mechanism of aromatic nucleophilic substitutions. In general, students, aromatic nucleophilic substitutions requires, first of all, a good nucleophile such as one carrying oxygen, nitrogen or cyanide group. Secondly, a good leaving group such as one of the halides, that is a fluorine, chlorine, bromine or iodine. Third, an electron withdrawing substituent on the benzene ring, which can be of the type like carbonyl nitro group, cyanide groups located ortho or para to the leaving group. The mechanism of aromatic nucleophilic substitution can be divided into two major sets. One which follows second order kinetics and one which follows first order kinetics. First, we shall pay attention to the reactions that follow the second order kinetics. Thus, the rate of reaction is determined by the concentration of both the reactant as well as the nucleophile. So, this makes the reaction second order. Mechanistically, second order nucleophilic aromatic substitutions can be of the following two types. First would be addition-elimination mechanism, which follows the second order kinetics, and second would be the elimination-addition mechanism, which follows the second order kinetics. Now, first we would look into the addition-elimination mechanism of nucleophilic aromatic substitution following second order kinetics. Alkyl halides are common substrates reported to undergo aromatic nucleophilic substitution reactions, commonly abbreviated as SNAr reactions, is a general schematic representation for addition-elimination reaction in case of aromatic nucleophilic substitution. Now you can see It is clear from this figure that it is a two-step reaction, wherein in the first step the incoming nucleophile attacks at the same position where the leaving group is attached. Such attack is known as ipso attack, and we have taken this up in detail in the previous modules. In the subsequent step or the second step of this reaction, that is addition-elimination mechanism, the leaving group gets detached, leading to regeneration of aromaticity in the benzene ring or the phenyl ring. Now, as mentioned before, for such mechanisms, suitable electron withdrawing group on the substrate favors the reaction, as they can stabilize the intermediate carbon ion which is formed, because electron withdrawing groups tend to pull away the electrons from the benzene ring. So, they would nullify or they can stabilize, as you can say, the excess negative charge on the benzene ring. Evidence for this mechanism was known as early as in 1902, when a stable intermediate for the following reaction between 2,4,6 trinitrophenitol and methoxide ion was isolated. Now, it is very interesting to know, students, that intermediates of this type are stable salts, and they are popularly known as Mesenheimer salts or Mesenheimer-Jackson salts. Now, you can see the formation of Mesenheimer-Jackson salt in case of 2,4,6 trinitrophenitol. Till date, students, a great number of such complex intermediates have been isolated and have been characterized by latest techniques like NMR and X-ray. Nucleophilic aromatic substitution occurs with a variety of strong nucleophiles, which includes the hydroxyl ion, the OR, that is the ether molecule, the NH2, that is the amine, the SR, that is the thioether, ammonia NH3, and aliphatic amines like RNH2. For these reactions, the reactivity of nucleophiles is significantly enhanced if the reaction is carried out in polar aprotic solvents. That means the solvents are having polarity, but they are aprotic. That means they do not have hydrogen ions attached to in the solvent as a part of the solvent. In polar solvents, like polar aprotic solvents, that is, the incoming nucleophile anion becomes soluble, though it may not get stabilized by hydrogen bonds, because it is a polar aprotic solvent. Further, the position of substituent that best facilitates the reaction is ortho or para substitution. Now, the reason for this is that the negative charge acquired by the ring may get accommodated by the substituent. In contrast, if the substituent is present at the meta position, no such stabilization by the substituent is achieved. This becomes clearer from the following resonating structures, that if it is present on the ortho or para position, then the negative charge is stabilized. However, the charge is not stabilized that much if the position is meta. Students, it is good to note that the increasing number of electron withdrawing groups also increase the reactivity of aryl halides drastically towards nucleophilic substitutions. To have a close look at the statement which I stated just before, you can see this figure increasing the rate of reaction with sodium methoxide in methanol at 50 degrees Celsius. These are the reaction condition, and you can see the increasing rate of reaction as you increase the number of electron withdrawing groups in chlorobenzene. For say chlorobenzene, if the relative rate is 1, then para-nitrochlorobenzene will have a rate of 7 into 10 raised to power 10 as compared to chlorobenzene. So now you can see that just the presence of one electron withdrawing group at para position increases the reaction by drastically to a large value. Now consider 2,4-dinitrochlorobenzene, and you can see the increase is 2.4 into 10 raised to power 15 times as compared to chlorobenzene. Now if all the positions, that means 2 ortho and 1 para position, is occupied by electron withdrawing groups such as nitro, that is 2, 4 and 6 chlorobenzene. Now lastly, if all the 3 positions, that is 2, 4 and 6 trinitrochlorobenzene is considered, then the reaction rate is too fast to be measured. So you can imagine the effect of electron withdrawing group on the rate of reaction when a particular reaction conditions are specified towards aromatic nucleophilic substitution. Now students, according to the Hammond postulate, electron withdrawing groups stabilize the intermediate carbanion by lowering the energy of the transition state. Interestingly, increasing the electronegativity of the halogen atom in substrates increases the reactivity of the corresponding aryl halide. This trend is opposite to reactivity for aliphatic nucleophilic substitution, but the reason behind this is that a more electronegative halogen stabilizes the intermediate carbanion better by an inductive effect. Thus, students, you can realize that in case of halides, fluorine is the most electronegative. Then aryl fluorides are much reactive than other aryl halides like aryl chloride, aryl bromide and aryl iodide respectively, which contain lesser electronegative halogens as compared to fluorine. The SNAr reactions, they follow a second order kinetics as already discussed according to the following rate equation. That is, a rate is equal to K, that is a rate constant, the concentration of aryl halide and the concentration of nucleophile. Now if you see the following data in this table, this illustrates the significant differences observed between a reactivity of alkyl halides. Now you can see, if you have a para-nitroaryl halide, then in case if the halide is fluorine, then the reactivity is 312. In case of chlorine, it is 1, for bromine it is 0.8, and for iodide it is the least, because it is the least electronegative halide, it is 0.4, and the reaction conditions are same, that is sodium methoxide in methanol at 50 degrees Celsius. Now as can be seen again from the table, the reactivity of substituted aryl fluoride is almost 780 times more as compared to aryl iodide. Following diagram, as you can see here, presents the reaction coordinates for a general aromatic nucleophilic substitution, that is SNAr reaction. Now as you can see, the formation of intermediates in 2 transition states and further the formation of products, and how the regain of stabilization is there in the transition states. As can be seen, it follows 2 steps in the transition states, that is 2 transition states for 2 consecutive steps that are involved in this reaction, because it follows a second order kinetics. Now let us take a specific example. The Chichi-Babin reaction exemplified below, as you can see in the figure, is a nice example of second order addition-elimination aromatic nucleophilic substitution reactions as we have been talking about. In this reaction, students, note that pyridine is attacked by a strong nucleophile, that is amide, that is NH2 minus, which displaces hydride ion On treatment with water, the desired 2-aminopyridine is obtained. Another name reaction involving nucleophilic aromatic substitution is the very famous von Richter rearrangement. It involves a reaction of substituted aromatic nitro compounds with potassium cyanide to give rise to carboxylation of ortho position relative to the leaving nitro group. Now, the mechanism of this reaction is clearly given to you here. These are extremely useful reactions to bring about the introduction of carboxylic acid functionality in the aryl ring. That means the important reactions are von Richter reaction as well as the Chichi-Babin reaction, which we have discussed in detail. Now, let us come to the second series of aromatic nucleophilic substitution reactions, which follow, instead of addition-elimination, they follow the elimination-addition mechanism, again which follow the second order kinetics. Without a substituent, it is hard for aryl halides to undergo nucleophilic substitution, and only under drastic condition they react with nucleophiles. For example, students, chlorobenzene can be converted into phenol by reacting it with sodium hydroxide above 300 degrees Celsius. Now, that is a very harsh reaction condition and at 170 atmosphere pressure. Now, if you see, the reaction is given here to you as well as the reaction conditions, and you can perceive how harsh the reaction conditions are there to actually carry out the nucleophilic aromatic substitution for the conversion of chlorobenzene into phenol. Yet, in another reaction, para-chlorotoluene with strong base, that is sodamide or sodium amide you can say, leads to the formation of para and meta substitution products. Now, sodium amide is a very strong base. This result was surprising and was explained by the fact that nucleophilic attacks on reaction intermediate at either C3 or C4 position. Such reaction conditions or such reactions indicate that nucleophilic aromatic substitution by an elimination-addition mechanism leads to products with substitution on the carbon directly bonded to the leaving group or the carbon which is adjacent to it. Now, students, to illustrate what I said just now, you can see this example that in case of para-chlorotoluene, you can see that with a strong base, that is NaNH2 soda amide, it leads to the formation of para and meta substituted products. Now, this is clearly shown here to you, that is it takes place adjacent to the leaving group or on the leaving group. These elimination addition reactions proceed via benzyne intermediates. The benzyne intermediate has a triple bond in the benzene ring during the transition state. The triple bond in the benzyne is unusual as each carbon of the 6-member ring is sp2 hybridized, and as a result the sigma bond and 2 pi bonds of the triple bond are formed with the overlapping orbitals. Although benzyne intermediate is best described as to having a strained triple bond, a biradical representation is also sometimes useful and describes properties of the system. Now, students, benzyne intermediates are highly reactive and they readily undergo nucleophilic substitution reactions. Now, there are many kinds of benzyne intermediates which can be formed. You can see here the ortho, meta and para benzyne structures. Now, as I said that benzyne intermediates are highly reactive and they readily undergo nucleophilic substitution reactions. Due to their high reactivity, benzyne intermediates are synthetically very useful to prepare various useful products. There are alternate ways to prepare benzynes, and thus the formed benzynes are used as diene components also to carry out the much famous Diels-Alder reaction. Now, as you can see, here is an example of the Diels-Alder reaction. In this case, the benzyne intermediate will be formed and thus it reacts with 1,3-cyclohexadiene to give you a Diels-Alder adduct as given in the product. Here it is given in the 46% yield. Benzyne undergoes Diels-Alder reaction with anthracene to give a symmetrical cage structure. Now, you can see here again, if you consider this kind of benzyne and the anthracene, you can see how much symmetrical cage structure is obtained. Now, you can now realize that how important the benzyne intermediate is. Apart from it being an intermediate in the nucleophilic aromatic substitution, it is also useful in the Diels-Alder reaction. Now, students, let us come to the SN1 mechanism for nucleophilic aromatic substitution. Just as a reiteration, I would like to tell you that till now we have studied the SNAr mechanism for nucleophilic aromatic substitution as well as the benzyne mechanism for the same. Now, coming on to the SN1 mechanism. The SN1 mechanism represents first order nucleophilic substitution reactions. Now, again I would like to tell here as a reminder that both benzyne and SNAr mechanisms were the second order kinetics mechanism and SN1 is the first order nucleophilic substitution reactions, where the rate of reaction depends only upon the nature of substrate and no effect of concentration of incoming nucleophile is observed in this case. Such substrates are rare to find unless highly substituted benzene rings are present or with diazonium salts. When primary aromatic amines are treated with nitrous acid, that is HNO2, under cold conditions, that means the cold conditions are 1 to 5 degrees Celsius, they give diazonium salts and these salts are used to prepare various dyes which are very useful commercially. These diazonium salts are good substrates for reactions proceeding via the SN1 mechanisms. This is because in diazonium salts the leaving group is a dinitrogen, which is an excellent leaving group, and on leaving it affords a positive charge on the benzene ring, making it available for the attack by the incoming nucleophiles. Now, you can see here how the intermediates are formed and how it follows a first order kinetics. Following are the few reactions of benzonium cation formed by diazonium salts. Now, you can see how the benzonium cation is useful for the formation of many products. As can be seen, students, these are very useful reactions in chemistry which afford the introduction of variety of functional groups on the benzene ring under relatively mild conditions, and they can be used for the formation of many other products, considering them as the starting products. Now, students, after having studied the SNAr mechanism, the benzyne mechanism which fall under the second order kinetics, and the SN1 mechanism which falls under the first order kinetics in substitution aromatic nucleophilic compounds reactions, we taught you in this module that aromatic nucleophilic substitution reactions involve attack of nucleophile on the substituted aromatic rings and thus are relatively rare. Based on the order of reaction, aromatic nucleophilic substitutions are classified as unimolecular or bimolecular reactions, that is following first order or second order kinetics. Bimolecular SNAr reactions operate via two mechanisms. First one we taught you was addition-elimination and the second one was elimination-addition. The addition-elimination was also called as SNAr and the elimination-addition was called as Benzyne mechanism. Mesenheimer complexes or Mesenheimer-Jackson salts are 1:1 reaction adducts, intermediates in bimolecular nucleophilic aromatic substitution that are stable and isolated as early as in 1902. Next we taught you that aromatic nucleophilic substitutions are favored by electron withdrawing substituents on benzene ring and good leaving groups. Also, benzynes are highly reactive and are synthetically useful intermediates with a strained triple bond in the benzene ring. They also possess some biradical character. Benzyne mechanism gives rise to reduced selectivity in product formation, as is seen in case of formation of Diels-Alder adduct. For unimolecular aromatic nucleophilic substitution, diazonium salts are good substrates as dinitrogen is a good leaving group. A number of useful name reactions such as Chichi-Beben reaction and von Richter rearrangement involve aromatic nucleophilic substitution mechanisms. Now students, I really hope that you found this particular module on nucleophilic aromatic substitution very useful.